Hey everyone, this is Matt with Learn Everything About Design, and in this video we're going to talk about storing energy in 3D prints, we're going to talk about the design process, and we're going to launch some Q-tips. Well, so this is not our typical how-to video because honestly the CAD part of this is pretty straightforward. But what we want to focus on is all the surrounding information about design in general that we need to know to tackle a project like this. Now when I say project like this, what do I actually mean? Well, a while ago, I came up with a Q-tip bow for my kids. Now, this is a simple project that you can do with a couple of 3D printed parts and a rubber band. You can set up some rings on the ground and make a little game out of where these Q-tips are going to land. Now, the process uses a rubber band to store energy and launch the Q-tip. Now, this works pretty well. It shoots about 10 to 15 feet, and there are all kinds of different parameters you can change. How much you can pull the rubber band back, what size rubber band you use, and how the mechanism itself works. So using some basic parameters and a rubber band, we can make a device that can launch a Q-tip about 15 feet. But my kids being my kids, watching a Mark Rober video, we're talking about the world's smallest 3D printed Nerf gun. Now, Mark doesn't need any help from me getting views, but I will put a link to his video if you haven't seen it. It's pretty interesting information. But what they did on their channel is they used a 3D print to store the energy because they were trying to scale down a Nerf gun. Now, this is a tough process because Nerf guns and mechanisms in general will have a lot of moving parts. And when you start to scale stuff down to small sizes, then assembly becomes a challenge and just making the parts is tough in general. So what they did was they used a 3D print to store the energy as a spring and use that to launch a little dart. So having seen this, I thought, well, maybe I can apply that to making another variation of this Q-tip launcher. Enter the Q-tip blaster. Now, I set out to see if this was possible, and it is, but it's not as good as using a rubber band. But that didn't stop me from exploring the process, and we're going to talk about it here. But ultimately, we've got a single 3D printed part. We can pull it back and we can launch a Q-tip. So mission accomplished, but what are the things that we had to understand and know in order to make this happen? So the first thing that we should understand is we need to know about storing energy. When we think about a projectile, in this case a Q-tip, we need an initial force to be able to push it. Now the initial force can be stored in all sorts of things: springs, rubber bands, air pressure, flywheels, or in our case, the 3D print. When we think about storing energy, we need to understand that there is a conservation here, meaning that we need that energy to come from somewhere. If we just throw it, that's one way that we put energy into the system. If you think about a flywheel, a simple example is a yo-yo. When we have a yo-yo and we just let it drop, as the yo-yo spins, it's storing that energy up and it's using it to come back up the string. Well, if you throw the yo-yo down, you're adding more energy to that system, and ultimately you're allowing it to spin faster, store that energy up, and come back up the string. Well, that's not really feasible for us to launch a Q-tip, but there are many other ways that we can think about storing energy in these systems. So in our case, we've got a simple version that uses a rubber band, and we want to convert a spring force stored inside of a 3D print. In order to do that, what do we need to know? Well, first we need to set a baseline. We're only using hyper PLA material. Of course, we could use PETG or ABS and we would get different results, but we need to have a baseline to do some testing and figure out what our limits are. In addition to that, we also need to have a basic understanding of material properties. Now, we're not going to go deep into math or taking a look at the material properties here, but we need to understand a couple of basics. When we're talking about materials, we want to talk about three main regions of material properties. We've got our elastic deformation, we've got plastic deformation, and we've got our failure point. Now with elastic deformation, this is where we can bend our part and have it return back to its original shape. Now some materials are much better at this than others. Spring steel, for example, is much better than using something like plastic. The second region is going to be our plastic deformation, also known as yield. Now the plastic deformation is where the part will be bent or deformed and it will no longer return back to its original shape. Now it's called plastic deformation because honestly plastic is not a good spring, so we're already at a disadvantage here. And the third area that we want to focus on is the actual failure point of our material. Now the failure point, or exceeding the tensile strength, is where we're going to bend our part, And not only will it no longer return to its original shape, but it will actually fracture and break apart. So these are the areas that we need to work within when we're thinking about our materials. Now, unfortunately, we're not just dealing with plastic, but we're dealing with 3D printed plastic. Now that means that you should do some simple tests. Come up with a couple of basic shapes, print them, and test them out. Now, in my case, what I did was I printed a small section that was 50 millimeters long, 1.2 millimeters tall, and a little bit like 4 millimeters wide. I printed it so that all the traces were horizontal, and then I printed it up on end. And doing some testing, it actually performs differently based on the layer orientation. So knowing that, we have an initial thing that we need to understand, and that's that our layer orientation is going to have an impact on how well this thing works. The next thing that we need to figure out is what our basic parameters are and what our limits are. But before we can even get into that, it's important that we think about the scientific method in general. Now with the scientific method, and we're not going to go through every step here, but having a good understanding of what information already exists as your starting point is where you should usually begin. Now, thankfully, Mark already did some work for us and they designed a mechanism that worked. So the first step was to replicate that. So what I did was I modeled something very similar, printed it, and tested it out. What I found is that I'm using a standard 0.4 millimeter nozzle, and this limits the width of my traces. And in my initial test, the smallest that I could make those traces was too small. It just broke. It worked, but it wasn't going to be robust enough for what I was trying to do. So that began the next couple of tests. Looking at the way that they did their design, I thought, well, I surely could simplify this a bit. So I initially started with a simple repeating V shape with just a single spring in between each V. I played around with different widths from 0.4 to 0.8 to 1.2, which is 1, 2, and 3 traces of the 3D printer. And I figured out what my limits were and what the overall range of sizes was that I should work with. And what I ended up with is that 2 traces are 0.8 millimeters wide, and about the overall height of 1.2 millimeters gave me the best results. Now with that information, I thought I had it all solved, so I got to designing a small variation of this thing I thought would work. Well, that was a bit of false confidence because unfortunately, I didn't realize that I made some happy mistakes in the initial tests that worked, but I didn't understand why they worked. So what I ended up finding by going back to the drawing board was that not only did I need to have that 0.8 millimeter wide section, 1.2 millimeters tall, but ultimately it needed to be longer than my second tests, and the outside frame of the part actually needed to flex inward. So I began doing a couple more tests. Now, I say a couple, I probably printed 20 variations of this thing. Now, ultimately what I ended up finding out was that not only did the spring pieces need to be 0.8 millimeters wide, they needed to be at least 20 millimeters long. That 20 millimeters allowed them to deform in the middle to store that energy, and it resisted having too much stress on the outside edges where it connected to the rest of my part. But in addition to that, I also needed those outside sections to flex inwards. That was a key part of this, and allowing it to perform to store the energy and not get into that plastic deformation range. Once all that was sorted, I went through a couple of more design variations, playing around with a couple of parameters and figuring out ultimately what worked. Now, is this the most optimized version? No, I'm sure we could do more, play around with a couple of different areas, but what I found was ultimately using that repeating V and keeping it about 30 degrees allowed me to get the amount of travel I needed to store the energy and provide a stop to prevent me from getting into that plastic deformation range. Using these basic parameters, everything I had to figure out with all the testing, gave me a final device that actually worked. Now, ultimately, I was only able to shoot it about 6 to 10 feet at best, and the rubber band version shot 10 to 15 feet. So performance-wise, it's just not quite there. But it is a simple mechanism. It does have a lot of promise. Maybe with some different materials and some more testing, we'd be able to get a better result. But again, the rubber band variation is not optimized either. There's certainly more energy in that system that could be used. So at the end of the day, what does all this mean? Well, when we look at a problem and we're trying to make a solution, we need to think about the information that we have available to us, what solutions already exist, and how can we make them better. So in this case, we knew that we wanted to store energy in the 3D print, so we had to do a lot of testing to figure out what the criteria and the limits were of the material that we had available. Once we figured out those limits, we were able to begin refining the design and coming up with a final solution. Knowing that Mark and his team had already produced a variation of a mechanism that worked, made me realize that the system can perform, it can work. Maybe it's not optimized, but it is certainly possible. Now with all that information, we have a final result. And again, you can go to the description of the video. You can download both the bow as well as the little blaster. You can print them and test them out for yourself and make adjustments and refinements and see if you can optimize your own system. But ultimately, this mechanism does have promise in other areas. It could be used on a latch for a container or any other 3D printed mechanism where you just need a small or simple set of motion and allow it to return back to its original shape. So what do you think that you could do with this design? Is there more variations of this? Is there improvements to be had? And if you do make those variations and improvements and you want to share them, you can go ahead and drop me an email, support@cadeducator.com. If you like this style of video and you want to see more, please let me know in the comments as well. And again, it's always appreciated if you like and subscribe to the channel. We are updating content all the time, multiple times a week, and we do our best to answer every question that comes in through email. So as always, thanks for watching, and we'll see you in the next one.